We've looked at two types of conjectures involving monomial traces. The evaluation of monomial immanence at totally non-negative matrices and the evaluation of monomial traces at Kajtan-Lustig basis elements. These two conjectures we've seen are in some sense the strongest possible. Let's look at them closely so that I can explain how they're the strongest possible. So recall the Stembridge conjecture first. So that conjecture is that monomial trace immanence of totally non-negative matrices are non-negative for all partitions N and for all totally non-negative matrices A. Now Stembridge proved a partial result involving monomial trace immanence. And that actually involves the Kajtan-Lustig basis with q equals 1, because Stembridge is working with q equals 1. He proved that if we take the monomial trace indexed by lambda and we evaluate that at the Kajtan-Lustig basis element indexed by the longest element in the Young subgroup of type mu, that equals a product of the factorials of the parts of mu if lambda equals mu and 0 otherwise. So W mu is the longest element of the Young subgroup S mu, and that is the product of reversals on the interval 1 to mu 1 plus 1 to mu 1 plus mu 2, etc. Now the relationship between this result and immanence is that we can define a planar network d mu, which has a star of size mu1, star of size mu2, etc. So all these stars stacked on top of each other. And then this has the path matrix. So these are sources 1 through mu1 down here. So we'll have paths from every one of these sources to every one of the corresponding sinks. So that'll be an all ones submatrix. Let me write that J mu1. And then we'll have another block matrix for this star. Let's call that J mu2, again all ones. So we have this block diagonal matrix with these blocks of ones on the diagonal and zeros everywhere else. So we're going to look at taking immanence of this matrix, and let's look at the planar network. So Z of this planar network, that is the sum of types of path families where pi covers the planar network. That's going to be everything in the Young subgroup S mu, because we've got the longest element where everything goes straight through an intersection, and then we have the identity where there's no crossings at all and everything in between. So this is equal to the sum of V less than or equal to that longest element in the Young subgroup, V, which is just a Cauchy-Johnlistic basis element indexed by W mu. Now let's give this planar network a name. I mean the path matrix. Normally I would just call it A, but I want to call it A mu to emphasize that it came from this planar network D mu. It turns out that if we apply any eminent indexed by a trace to A mu, then we get that trace applied to the Cauchy-Johnlistic basis element C indexed by W mu. And the reason is that by Stenberg's result from another lecture, let's say Stenberg's result on skeletons, we have that the theta imminent of A mu is a sum over all bijective skeletons K that is a multi-set of edges that could be covered by a path family from all the sources to all the sinks. Weight of that bijective skeleton times theta applied to Z of that bijective skeleton, where Z is the sum of the types of all the path families that cover the bijective skeleton. Now if we look for bijective skeletons in D, well, this already is a bijective skeleton. It's already a union of n paths from all the sources to all the sinks. In fact, there's no subnetwork that is also a bijective skeleton. So that's the only bijective skeleton that there is. So we don't need the sum anymore. Now the weight of D mu is just 1 because we didn't put any weights on the edges. And we said that Z of D mu is just the Cauchy-Johnlistic basis element indexed by W mu. So we've got one term in the sum, which is 1 times theta of that Cauchy-Johnlistic basis element, which is all we're claiming. All right, now this result tells us a lot about which imminents could possibly have the property that when we evaluate them on totally non-negative matrices, we always get a non-negative number. So let's let script T of Sn be the trace space. of Sn. And I can't remember if I've given it scalars before, if I decided that they were real numbers or integers. So let me choose integers now. So let's say this is the integer span of whatever your favorite trace basis is. Might as well choose the irreducible characters. And now I claim that we cannot have the theta imminent of A being greater than or equal to 0 for all totally non-negative matrices A. Well, I'm assuming that here theta is in the trace space. So for theta in the trace space, we can't have the theta imminent evaluating non-negatively on all totally non-negative matrices unless theta belongs to the non-negative integer span of monomial traces. And the reason is, so let's suppose that theta is a sum of b lambda phi lambda with b mu less than 0 for some mu. So then the theta imminent of A mu equals theta of the Cauchy-Analytic basis element indexed by W mu. And theta is this sum of this linear combination of monomial traces. But we said before that the monomial trace indexed by lambda evaluated on this Cauchy-Analytic basis element indexed by the longest element in the Young subgroup S mu is going to be either 0 or it's going to be a product of the factorials of the parts of mu. So there's only one term in this sum that's not 0. And that's the mu term, b mu. And then we get mu1 factorial, mu2 factorial, etc. These are all positive integers, but if b mu is negative, then this is negative. So we just got that the evaluation of this theta imminent at the matrix A mu is negative. Thus we can say that the Stembridge conjecture about monomial trace imminence can be stated as the Stembridge conjecture is equivalent to the statement that the theta imminent of A is greater than or equal to 0 for all totally non-negative A. If and only if theta belongs to the non-negative span of monomial traces. Alright, so the only imminents that could possibly have this property are the ones that are non-negative linear combinations of the monomial trace imminents. So if those monomial trace imminents have this property, there's no stronger property. There's no other imminents that have it unless it's a consequence of the monomial imminents having that property. Alright, now let's look at Haymann's conjecture. That is that if we take the monomial trace of the Hecke algebra and evaluate that on any Cauchy-Lustig basis element, that should give a polynomial in Q with non-negative integer coefficients. So for all lambda partitioning n and for all w in the symmetric group. Now Hayman proved a Q analog of Stembridge's evaluation result. And that is, if we take the monomial trace indexed by lambda and evaluate that at the Cauchy-Lustig basis element indexed by the largest element, the longest element in the Young subgroup S mu, then that equals a product of Q analogs of factorials. Or 0, depending on whether lambda and mu are equal to each other. So the first case is lambda equal to mu, and the second case lambda and mu not equal. Now let's let script T of HNQ be the trace space of the Hecke algebra. And again, I can't remember what scalars I assigned to this, if any, but let's say this is integer linear combinations of the irreducible characters of the Hecke algebra. So this conjecture is best possible in the sense that if we have some other trace then it's impossible to have that trace evaluate non-negatively on all the Cauchy-Lustig basis elements. Unless that trace is a non-negative linear combination of monomial traces. So to see this let's suppose that theta q is some linear combination b lambda phi lambda. And let's suppose that b mu is less than 0 for some mu. Then theta q of the Cauchy-Johnson basis element indexed by w mu equals the sum of b lambda phi lambda evaluated at that element. But this is either going to be 0 or a product of factorials here. So we can forget about all the terms that are not 0. Sorry, forget about all the terms that are 0. That is, forget about all the partitions lambda that are not mu and just look at the mu one. So we've got b mu times mu1 q factorial up to mu r q factorial. But if b mu is a negative integer, and these are all polynomials in Q with positive integer coefficients, then we get a polynomial with all negative integer coefficients. So that cannot evaluate non-negatively on every Cauchy-Johnson basis element if it doesn't evaluate non-negatively on this one. So this means that Haymann's conjecture can be stated equivalently as assuming that theta is a trace theta q of the Cauchy-Johnson basis element is a polynomial in Q with non-negative integer coefficients for all W and Sn if and only if this trace belongs to the non-negative span of the monomial traces. And just to remind you, all the other traces that we know essentially, except for the forgotten traces, are non-negative linear combinations of the monomial traces. We know that for irreducible characters, we do get an evaluation. It's a polynomial in Q with non-negative integer coefficients, and therefore for induced sign characters and induced trivial characters also, because those are non-negative linear combinations of irreducible characters. Power sum traces are non-negative linear combinations of monomial traces, but they're not known to evaluate non-negatively on all Cauchy-Johnson basis elements. So that proving that would be a weaker result than proving this. The end.